Hey everyone, let's jump right into this explainer. Today we're decoding a seriously incredible breakthrough in how AI is being deployed to stop a massive, rapidly evolving digital crime wave. We're looking at some fascinating new research that takes a completely novel approach to cybersecurity. Literally, they're turning malicious code into pictures to catch the stuff that traditional security systems are completely missing. Think for a second about the sheer scale of the Internet of Things right now. We're digitizing our world at a staggering pace. And I'm not just talking about your smart home locks or your connected fridge, right? We're talking about critical infrastructure. Hospital cardiac monitors, GPS-controlled agricultural equipment, autonomous manufacturing drones. And here's the terrifying reality. Hackers know these devices are coming online way faster than we can secure them. It's effectively turning them into highly vulnerable ticking time bombs. Which brings us to Section 1, the IoT Malware Crime Wave. IoT devices present these entirely new, highly vulnerable attack vectors compared to traditional computers. As this quote from the researchers brilliantly illustrates, the stakes in cybersecurity just aren't purely financial anymore. Sure, when ransomware hits a desktop PC, it's a huge headache. But when a malware attack targets an IoT medical device or an industrial control system, human lives are actually on the line. The damage leaps from the digital realm straight into the physical world. All right, let's move to Section 2, the obfuscation blind spot. So if the stakes are this high, why exactly are our current defense systems failing to stop these attacks? Well, it's because modern malware acts like a master of disguise. Think of traditional malware detection models like a detective wearing an eye patch. They're generally single-input systems, meaning they usually only look at one file type, typically just the raw byte data. But today's hackers, they use metamorphic malware. This is shape-shifting code that uses advanced obfuscation to hide its malicious intent. If a hacker decides to hide the bad instructions in the assembly code rather than the bytecode, a traditional scanner simply won't see it. It sneaks right past that blind spot. This leads us directly to Section 3, a tale of two files. And this is the absolute crux of the researchers' discovery. They suspected that malware leaves entirely different visual footprints depending on exactly where you look. So they took the exact same piece of malware, a known strain called obfuscator.ac, and they converted its data into 1D images. On the left, you've got the visual representation of its assembly file, and on the right, its byte file. Notice how they look completely different? They exhibit entirely unique characteristics. So if your security system is only trained to look at the image on the right, it is totally blind to the complex patterns happening on the left. Now, you might be wondering, why even turn code into images in the first place? Well, raw malware lacks a standard structure, which makes it incredibly hard to parse. To catch these cybercriminals, the researchers extracted the hexadecimal and assembly code and actually unrolled it into one-dimensional grayscale images. It's kind of like mapping out a DNA sequence. This specific 1D transformation is totally genius because it perfectly preserves the chronological sequential flow of the malware's behavior without losing those crucial hidden features that get stripped out in standard analysis methods. Okay, let's dive into Section 4, Meet the HCL-classifier. Now that we found the clues, those hidden visual patterns in the two different file types, let's introduce the fully equipped detective built specifically to read them. Meet the Hybrid Convolutional and Long Short-Term Memory Classifier, or the HCL classifier. Instead of just one input, this grand architecture features two parallel pathways. It takes both the byte images and the assembly images and analyzes them simultaneously. Finally, we've got two eyes looking at the problem. Here's how this whole process builds, step by step. First, the dual 1D images are inputted. Next, a convolutional neural network, or CNN, acts as a high-powered magnifying glass to automatically extract spatial clues. And then finally, a Bi-LSTM network acts as the brain, reading the sequence of events over time to definitively classify exactly what family of malware we're dealing with. Let's take a closer look at that magnifying glass. This is the convolution block. What's so incredible here is that it automatically selects these spatial features without needing human expertise or intricate manual feature engineering. It runs the images through multiple layers of filters and max pulls, capping it off with a global max pulling layer. This ensures it perfectly translates the spatial patterns of the malware, regardless of where the hacker tried to hide the code. And then here is the brain, the Bi-LSTM block. This bidirectional long short-time memory network takes those spatial clues and analyzes them over time. And notice the arrows in the diagram here. It trains both forwards and backwards. By reading the sequence in both directions, it guarantees it catches every single complex, long-term pattern the malware exhibits. It bridges the time intervals of the attack sequence perfectly. Next up, Section 5, High Accuracy, Low Resources. So our AI detective has its dual magnifying glasses and its bidirectional brain. But how did it actually perform when put to the test against vast datasets of Microsoft and IoT malware? When researchers tested standard single-input models like the CNN-FC or CNN-RF, they performed decently, hitting around 97 or 98%. But in cybersecurity, a 1 or 2% gap is all a hacker needs to slip through. When they tested the dual-input HCL-classifier, it absolutely crushed the baseline metrics, achieving an astonishing 99.91% accuracy on Microsoft malware and 99.83% on IoT malware. So what does a number like that actually represent in the real world? A classification accuracy of over 99.8% effectively eliminates the blind spot that traditional models suffer from. It absolutely proves that by looking at both the byte and assembly files simultaneously, the malware has nowhere left to hide. If you want visual proof of this perfection, just look at these confusion matrices from the paper. See those dark green squares running diagonally down the chart? That represents the HCL classifier expertly categorizing complex, devastating IoT malware families like Mirai, Gafkite, and Hydra with near-perfect precision. It generated almost 0 false positives and 0 false negatives across thousands of samples. And here is the real kicker, which is incredibly vital for the Internet of Things. This massive AI brain doesn't require a supercomputer to run. The researchers proved it has a lightning-fast prediction time of just 0.004 seconds. It can even be trained and deployed on incredibly low-resource machines, like a basic Core i3 processor with just 2 gigabytes of RAM. It's specifically optimized for the tiny, constrained hardware that actually powers real-world smart grids and connected devices. All right, let's bring it all together in Section 6, A Safer Connected Future. Let's wrap this explainer up by looking at why this specific hybrid AI architecture fundamentally matters for our digital future. By proving once and for all that 2 eyes are better than 1, this research gives organizations a highly robust defense against shape-shifting cyber attacks. It provides cybersecurity students and professionals with a powerful, accessible blueprint for designing hybrid CNN and Bi-LSTM networks. And most importantly, it gives us a realistic, lightweight tool to secure our most critical infrastructure, ensuring that those life-saving hospital monitors and automated grids remain safe from malicious takeovers. I'll leave you with this provocative thought to ponder. If we can achieve this level of security by simply looking at 2 file types as 1D images, how else might we combine hybrid AI models to uncover the hidden fingerprints of tomorrow's threats? I highly encourage you to read the full paper from the article link in the journals provided in the description to explore the math and the fascinating AI architecture of the HCL classifier even further. Keep learning, stay curious, and I'll catch you in the next explainer.